Today's goal is to quantify the growth or decay of an exponential function. So to talk about different ways of describing how quickly the function is growing or decaying. Example 1. Suppose the population of squirrels in Central Park X years after 1980 can be modeled by this function. F of x equals 320 times 3 to the x over 11. What does the function tell us about the squirrel population and how it's changing over time? Well, just by looking at this function, we can say, well, the squirrel population must have been 320 squirrels in 1980, and that value must be tripling every 11 years. So in 1991, there would be 3 times as many as you started with, so 960 squirrels. And then in another 11 years, that value triples again. But if we want to talk about the annual increase or decrease in the squirrel population, annual means in 1 year. So if it's tripling over the course of 11 years, how much is it growing in a single year? Well, we can rewrite this function as f of x equals 320 times 3 to the 1/11th to the x power. It's like I'm taking the fraction of the exponent, the 1/11th, inside with the 3. And if you type into your calculator 3 to the power 1 over 11, you get something about 1.105. So if we write the function in this way, well, this is 100% of the original squirrel population plus an additional 10.5%. So this shows us that the squirrel population increases by about 10.5% each year. Name the doubling time of the squirrel population. Well, we started with 320 squirrels in 1980. So if we want to double that, we're going to take 320 and multiply by 2. So that gives us 640 squirrels at some moment in time. Our goal is to figure out what that moment in time was. How long did it take for the population of squirrels to double? Well, this is just an exponential equation, which we can solve by isolating the base and then rewriting it as a logarithmic equation. You can type into your calculator 11 times the log base 3 of 2, and you get that x is about 6.94. So the doubling time, it takes almost 7 years for the squirrel population to double. Last part of this example, make an annotated table of values that reinforces our conclusions from parts A through C. So if we're to make a table of values, in the first part, just by reading the original function, we said if we're starting out in the year 1980 with 320 populations, or 320 squirrels, that population will triple in 11 years. And indeed, if you look at a table of values and look at the x value 11, you see the y value 640. Oh, sorry about that. If you look at the x value 11, you should see the y value 960, which shows that over the course of 11 years, the population will triple. But then we found the annual increase and said the annual increase is 10.5%. Indeed, if you look at the x value 1, you get the y value 356.61, and the x value 2 gives you 643.8. And check with your calculator. This is what you'll get if you multiply the y values by 1.105. So if you don't want to wait 11 years to see what the squirrel population is doing, you can see in a single year, the squirrel population will increase by about 10.5%. And then finally, we said that the doubling time is about 7 years. So if you look at the x value 7, I'm drawing ellipses or dots in between because we're skipping some x values. But if you look at the x value 7, you see that the squirrel population is about 643.8, which is approximately double the squirrel population of 320. So these are 3 different ways of describing how quickly the squirrel population is growing. Whether you're patient and you're willing to wait until you can talk about it triples, or if you just want to know when will it double, or if you want to know how could we describe the change over the course of a single year. Example 2. What's the half-life of the radioactive substance whose mass in milligrams can be modeled by this function, T years after it's uncovered? So this must be some substance that's decaying, like carbon-14, which we use to date fossils and things like that. A naught is how we pronounce this. It looks like a capital letter A with a subscript of 0. This represents some initial or original, that's why we use 0, amount of time. Or amount of the substance. So we don't know how much of the substance you started with, but if we're looking for half-life, that's the amount of time that must pass before half of your substance is left. So if we started with some amount A naught, we want to end up with half of A naught, whatever that may be. And again, we've just got an exponential equation at this point, which we can solve by isolating the base. In this case, the A naughts will cancel out, so we're just left with 1/2 equals e to the negative 0.4t. Since we have the base alone, we can isolate, or we can convert into a logarithmic equation, and then isolate the variable. Grab your calculator. This will give you about 14.2 years. So what this means is however much of the substance you find. If you find 100 milligrams, after about 14 years, you'll only have 50 milligrams left. If you start by finding 30 milligrams, after about 14 years, now you'll only have 15 milligrams. So whatever your original amount is, you'll have half left after 14 years. Okay, here's your third example. The value of Ms. Mark's Beanie Baby collection X years after 2011 can be modeled by this function. Name the annual rate of change. Again, annual means in 1 year of her Beanie Baby collection. So we're going to take this exponent of 1/10 inside the multiplicative growth factor. And so in your calculators, type in 0.79 to the 1/10, and you should get 0.977 to the x. And if you subtract that from 1, you'll find that 0.977 is equal to 1 minus 0.023. So this would be about a 2.3% decrease in the value of her collection each year. And when we compare that to what we see just by examining the function notation, this is similar to example 1. We can see that there is 79% would be 1 minus 100% minus 21%, or 1 minus 0.21. So we could see that every 10 years, there's a 21% decrease in the value of her collection, or every single year, there's a 2.3% decrease in the value of her collection. If we want to interpret the average rate of change of the value of her collection over 2 different intervals, we can just choose. So let's say we want to know what's the average rate of change on the interval from 0 to 2. So you need f of 2 minus f of 0, which you can find by substituting. And you should get this as negative 5.53. And the average rate of change on a different interval, let's say maybe from 8 to 10, you take f of 10 minus f of 8, substitute to find those y values, then you're subtracting, and dividing, you get negative 4.58. If we're interpreting, here's how you interpret. This value tells us that on average, the value of her collection decreased $5.53 per year from the years 2011 to 2013. And this value tells us that on average, the value of her collection decreased $4.58 from the years 2019 to 2021. This is an additive rate of change, and we can see that her collection is decreasing in value, since these numbers are both negative, and it's decreasing at a decreasing rate, meaning it's decreasing faster here, and then as time goes on, these would be later years, the value of her collection is decreasing slower. So that's why we're reinforcing our conclusions from part C. Maybe this will be clearer even yet with a table, which is our last goal for the day. Here are all those values put together again. So in the year, we're calling this 0 since X is years since 2011. So meaning in the year 2011, her Beanie Baby collection was worth $240. And we saw that since it was to the power x over 10, that meant if you're willing to wait 10 years, you could see the value of her collection decreasing by 21%. And indeed, if you multiply 240 times 0.79, then you'll get this $189.60. But we also figured out an annual rate of change. So if you're looking 1 year later, her collection is worth $234.41. And if you want to do it again, 2 years later, her collection is worth $228.95. So if you want to see the annual rate of change, you can do so by this. We looked at the average rate of change, which meant we were looking at a subtracting rate. So if you subtract these, you notice that the rate of change isn't constant. Well, that makes sense. It's an exponential function. So the only way you're going to find a constant rate of change is by multiplying. Indeed, you could multiply by 0.977, which represents that 2.3% decrease. But here we can see that the values are decreasing by about $5.53. That was our average rate of change. Again, if you look at the x values from 8 to 9 to 10, there's not a constant additive difference, but there will be a constant multiplicative difference of 0.977.